In this section, I want to show you why the term simply connected is so important when we talk about line integrals and potential. Simply connected means that a set is connected and it has no holes. An example, this set is connected and simply connected, while if we remove something in between, something in the middle, then this ring is no more simply connected. Simply connected means that any closed curve can be continuously deformed into a single point without leaving the set. Let me start with the following example. Consider the function u as the function of x and y being arctangent of y divided by x. And just consider for the moment positive x and positive y to keep things as simple as possible. Then this is a well-behaving function of class C infinity, and we can compute the gradient, and we can call the gradient a vector field. So let's consider the vector field with the component f1 being the partial derivative of f with respect to u, and when we differentiate arctangent, we have 1 over 1 plus the square of the argument times the derivative of the inner function, which is minus 1 over x squared. We can simplify this a little to get minus fraction y x squared plus y squared. And the second component, f2, will be the partial derivative of u with respect to y. Once again, differentiating arctangent gives 1 over 1 plus y squared divided by x squared times the derivative of the inner function, which is this fraction, and differentiated with respect to y, we have 1 over x. And this can be simplified into a similar form if we multiply by 1 more x. We have x squared plus y squared, and we have x here. Well, now for this vector field, this is defined not just for positive x and positive y, for all xy with one single exception, the origin. So we could consider the condition xy being different from 0 and considering all the remaining points. But you see, if you take the plane and you remove one point, this set is no more simply connected. And one strange surprise, one unexpected problem will come out. We can check that this is indeed the vector field. This is indeed the conservative vector field if we consider the partial derivative of the first component with respect to the second variable. Then f1 with respect to y will be minus fraction x squared plus y squared squared, and here we have derivative of y, which is 1 times x squared plus y squared minus y times 2y is 2y squared. So we have minus y squared with minus x plus y squared minus x squared divided by x squared plus y squared square of that. And if we differentiate the second component f2 with respect to x, then again fraction x squared plus y squared squared, derivative of x is 1 times x squared plus y squared minus x times 2x is minus 2x squared, and this is indeed y squared minus x squared divided by x squared plus y squared square of that. And you see they are the same. They are the same in the whole plane R2 with the origin removed, which is not a simply connected set. If we forget about this condition, that the set should be simply connected, then we might expect that the line integral over any closed curve, over any loop, should be 0, right? Okay? Let's try a circle with radius r. With the parameterization, x is r cosine of 5 and y is r sine of 5. Then dx is minus r sine of phi d phi, and dy is r cosine of phi d phi. So the line integral over this circle with the center at the origin and radius r will be phi runs from 0 to 2 pi, one whole term, f1, which is here, minus fraction y is r sine of phi divided by r squared plus y squared, but in this parameterization r squared plus y squared is r squared times dx, which is minus r sine of phi d phi, we will write d phi at the very end, plus f2, which is fraction x, which is r cosine of phi, divided by x squared plus y squared, which is r squared, times dy, which is r cosine of phi. And this can be simplified. Minus minus gives plus. R times r is r squared divided by r squared is 1. Similarly here. And what remains is sine squared plus cosine squared, which is 1. So we have integral of 1 times d phi from 0 to 2 pi is 2 pi. You see? Different from 0. Isn't it strange? We have a conservative vector field. This is equal to this. And we have a closed loop, a closed curve. And still, the integral is not equal to 0. Well, formally, the reason is that considering this loop, we go around a missing point. The set is not simply connected. This example illustrates how important it is. Well, actually, this result can be justified, can be explained using some clever picture. Let's visualize this vector field. Let's start with another vector field, let's call it G, being just minus y, x. This is what we have in the numerator, and then we will consider the denominator. But for the moment, consider this a simplified vector field. That means at a given point xy, the vector field is minus yx, which is again a vector. And when we compare this vector with the position where we evaluate the vector field, this is a vector with the same length and perpendicular. Because the vector xy is perpendicular to minus yx. Because the scalar product is minus xy plus xy, which is 0. And two vectors with 0 dot product are orthogonal or perpendicular. So at this point, it goes, the first component is negative, it goes to the left, and it goes this way. And in all these points, goes this way. It's always perpendicular to the position, to the radius vector, to the vector connecting the origin with the point where we evaluate the vector field. And the length is the same, so if you go close to origin, it will be visualized by very short arrows. If you go far away from the origin, it will be a very large vector. Now, when we take this vector field and when we divide by r, then because this vector is proportional to r, if you divide by r, then you get a similar system of arrows, but with equal length, independent of how far we are from the origin. If we divide by r alone, but now we divide by r squared. That means we divide by r and once more by r. That means we get again a system of arrows that goes around, but now the arrows close to the origin will be large, and the arrows far away from the origin will be short. But still, there are tangent to the circle like that. So if we visualize this integral, then we have a vector field like that, and in each point, the force that we integrate is tangential to the journey, to the path. So the dot product of two vectors in the same direction is just the product of the magnitudes, of the norms of the vector. And because the modulus of this is constant, then we can consider the norm of the vector field, which is 1 over r, times the total length, which is 2 pi r. And if you multiply 1 over r with 2 pi r, the result is 2 pi, right? So if we want to get correct result, that means what we expect. If we want the line integral over closed curve to be 0, then we must choose some open, simply connected set. One possibility might be just the first quadrant. And then it is indeed true that for any closed curve in the first quadrant, the line integral of this vector field will be indeed 0. But the first quadrant is too restricting. We can perhaps consider the upper half plane. We can perhaps even add the third quadrant. We cannot add the complete fourth quadrant because then the set is no more simply connected. But if we take the plane and if we remove just one line, one half line, going from the origin to infinity in any direction, and we consider this set, then this is a simply connected set, and the integral of this vector field over any closed curve in this set, that means not containing origin and not crossing this deleted line, will be indeed 0. This will be still 0 even if we cross this deleted line in some careful way here's the origin. This is still 0, because if we remove this line, then the resulting set is open and simply connected. So you see the condition that curl of f being 0 in some simply connected set is very important, because if it fails to be simply connected, the conclusions might be incorrect.